Today we'll be doing chapter 11. These are the answers for today's questions. Questions 1. It is given that the mass of atom Fe is 55.934939 U. Mass of one proton is 1.007276 U. Mass of one neutron is 1.008665 U. And the mass of one electron is 0.0005486 U. A. Calculate the total mass of the constituent particles of Fe atom. Explain the discrepancy between the total mass of the constituent particles and that of the atom. B. Find the binding energy per nucleon of the ferrum atom. To determine the total mass of the constituent particles of ferrum atom, we need to add up the total mass of proton plus the total mass of electron plus the total mass of neutron. Now, atom is a neutral particles. Thus, in an atom, the amount of proton is equal to the amount of electron. How to determine the amounts of proton, electron, and neutron? We need to look at the mass numbers and also the atomic number. So by looking at the mass number and atomic numbers, we know that Fe atom consists of 26 proton, 26 electron, and 30 neutron. Now that we have all of the information needed, let us apply the equations M atom equals to ZMB plus ZME plus NMN. Substitute the values into the equations. I now have M atom equals to 56.4633896 U. The final answer should be in terms of U because the information given in the question is in terms of U, not kg. Now let us compare the two values, the mass of the ferrum atom and also the total mass of the constituent particles of the ferrum atom. So given the mass of the atom is 55.934939 U, the total mass of the constituent particles of the atom is 56.4633896 U. There is a slight difference between these two values. The total mass of the constituent particle is more than the mass of the atom because the energy is released when neutrons and protons they combine to form a nucleus. To calculate the binding energy per nucleon, we need to calculate the binding energy first. And to calculate binding energy, we need mass defect. The mass defect in these questions can be calculated by using the equations total mass of constituent particles of the atom minus the mass of the atom. So substitute the values into the equation. Mass defect is equals to 0.5284506 U. Now that you have mass defect, let us calculate the binding energy by using EB equals to delta mc squared. Substitute the values into the equations. Binding energy is equals to 492.25 MeV. Thus, the binding energy per nucleon EB over A is equals to 8.79 MeV per nucleon. Questions 2. A copper coin has a mass of 2.8 grams. The coin is entirely made of copper atoms. A. Calculate the energy required to break the nuclei of copper into its individual protons and neutrons. B. Calculate the total energy required to separate all of the neutrons and protons in this coin from one another. Given the mass of atom is 62.92960 U. Energy needed to separate all protons and neutrons in a nuclei is known as binding energy. And given the mass of atom is 62.92960 U, what we have to do before we calculate binding energy is to calculate the mass defect. But remember, when it comes to mass defect, we don't want the mass of atom. What we want is the mass of the nucleus. So mass of the nucleus can be calculated by using M nucleus equals to M atom minus ZME. Z can be obtained from the proton numbers in our questions. So M nucleus is then equals to 62.92960 minus 29 times 5.49 times 10 to the power of negative 4. This value can be obtained from the list of constants. So M nucleus is then equals to 62.913679 U. Next, let's calculate mass defect by using delta M equals to ZMP plus NMN minus M nucleus. Substitute the values into the equations. Mass defect is equals to 0.591964 U. Now that you have mass defect, we can then proceed to binding energy. So binding energy is equals to delta MC squared. Substitute the values into the equations, you will then obtain binding energy equals to 551.41 MeV. In previous questions, we calculated the energy needed to separate the protons and neutrons in one atom, which is equals to 551.41 MeV. In this question, it is asking for the total energy needed to separate all of the protons and the neutrons in one copper coin. Which means to solve this question, we need to find out how many atoms are there in a copper coin. So given the symbol Cu with a mass number 63 and an atomic number 29, so if you look at this value 63, which is the mass number, it gives us the information 1 mole of copper atom is equals to 63 grams. And if you look at the numbers of Avogadro, it tells us 1 mole of copper, it contains 6.02 times 10 to the power of 23 atoms. By using these two pieces of information, we can then determine 2.8 grams of copper contains how many atoms. So by using the ratio method that I showed you guys in the class, you can then obtain 2.8 grams of copper contains 2.68 times 10 to the power of 22 atoms. There is an alternative method that can be used to calculate the numbers of atoms in a copper coin. With the condition, the mass of the atom is given. So given the mass of the atom is 62.92960 U. If you look at the list of constants, it tells you 1 U is equals to 1.66 times 10 to the power of 27 kg. Thus, for every 1 copper atom, it is equals to 1.045 times 10 to the power of negative 25 kg. Therefore, 2.8 grams of copper atoms, it contains 2.68 times 10 to the power of 22 atoms. Now, the reasons why I show you this alternative method, because I want you to see what is the difference between the mass of one atom in terms of kg and in terms of U. And also, what is the difference between the mass of 1 gram of copper atoms and also the mole, 1 mole of copper atom. So make sure you don't get confused between 1 atom, 1 mole of copper atoms, and then 1 gram of copper atoms. So now that you have the numbers of atoms in the copper coin, you can then calculate the total energy by using EB times the total numbers of the atom, which is equals to 1.48 times 10 to the power of 25 MeV. Question 3. A radioactive sample contains 3.2 times 10 to the power of 18 atoms of a particular nuclide and it emits 3,600 alpha particles per second. Calculate the decay constant and half-life of the radioactive nuclide. If we go through the questions again, you'll see that the questions give you n equals to 3.2 times 10 to the 18 atoms. A equals to 3,600 particles per second. Therefore, you can determine the decay constant by applying equations. A equals to lambda n. Substitute the values into the equations. Lambda is equals to 1.125 times 10 to the power of negative 15 per second. The unit is per second because A given is in terms of second. Once you have decay constant, you can then determine the half-life by using T half-life equals to ln 2 over lambda. Substitute the values into the equations and half-life is then equals to 6.161 times 10 to the power of 14 second. Now again, the units in this question is second because your decay constant is as negative 1. Questions 4. 44 grams of petrified wood was found in a petrified forest. A sample shows a carbon activity of 100 decays per minute. If the half-life of carbon-14 is 5,730 years, and a freshly cut wood contains 6.5 times 10 to the power of 10 atoms of carbon per gram, how long has the tree been dead in terms of years? This question, it seems very short, but actually it contains quite a lot of information in it. So let us go through them one by one. First of all, you have to understand what does it mean by petrified wood and also what does it mean by freshly cut wood. So petrified wood, it gave us the current value, which is the final N and also the final A. Freshly cut wood, it gave us the initial value, which is the N node and also A node, if you have information related to it. And then the first piece of information given in the question is 44 grams. Why is it important to know how many grams of wood we have right now? That is because if you look at the question, it tells you 1 gram of freshly cut wood, it contains 6.5 times 10 to the power of 10 atoms of carbon-14. Therefore, for 44 grams, we have 2.86 times 10 to the power of 12 atoms. So the initial value N node is equals to 2.86 times 10 to the power of 12 atoms. Now, why can't we use the most method to calculate the numbers of atoms? Because now you are given a wood, but not all of the atoms inside it are carbon-14. They might have different types of atoms. Therefore, what we have to do, we have to use the information given in the question, which is 1 gram contains 6.5 times 10 to the power of 10 atoms to calculate the numbers of atoms inside this 44 gram. Okay, you cannot use the methods of a mole that we used in previous questions to calculate the numbers of atoms. Remember that. The second statement gave us the information about activity. Given a sample of petrified wood shows a carbon-14 activity of 100 decays per minute. Now, when it comes to these questions, what you have to do, you have to change it into SI unit. So A is equals to 100 decays per minute. It is equals to 100 decay over 1 minute. So if you substitute 1 minute with 60 seconds, you will then obtain A equals to 5 over 3 decays per second. Next statement gives us the information about half-life, where half-life of carbon-14 is 5,730 years. Now we're going to use it to calculate the decay constant. Remember, whenever you are given half-life, the questions always wants you to calculate the decay constant. So lambda equals to ln 2 over T half. And half-life, you need to change into SI unit. Therefore, I have half-life is equals to 5,730 times 365.25, that is the numbers of days in 1 year, times 24 hours in a day, times 60 minutes in 1 hour, times 60 seconds in 1 minute. So lambda is then equals to 3.83 times 10 to the power of negative 12 per second. Now that we are done analyzing the questions, let us think, how are we going to solve these questions? Now let's recall the information that we have right now. You have n initials and a final. When you have one initials value and one current value, then you cannot use it to solve the questions. What we have to do right now is we have to try to determine the values of a current n or initials activity. And we can do that because we have decay constant. So now let us use decay constant to find current n, which is our n final. So given a equals to negative dn over dt and n dn over dt equals to negative lambda n. So combine these two equations, we have a equals to lambda n. Substitute the values into the equations, n final is equals to 4.35 times 10 to the power of 11 atoms. Of course, if you don't want to use n final, you can also use the same method to determine the initial activity. But since I've already calculated the n final, so I'm going to stick to n in my remaining solutions. So now let's apply the equations for radioactivity decay. N equals to n naught exponential negative lambda t. Rearrange the equations. Exponential negative lambda t is equals to n over n. And I'm going to rearrange it one more times. So I have negative lambda t equals to ln n over n naught. So substitute the values into the equations. I then have t equals to 4.917 times 10 to the power of 11 seconds. But remember, the questions wants the final answer in years. Therefore, you have to convert the unit from second to years. So if you got it right, then t is equals to 1.56 times 10 to the power of 4 years. So that is the final answer for questions 4. So that's all in chapter 11, and that's all for this semester. Good luck in your PSPM exam.